Hey guys, my friend Josh just tweeted that he was parallelogramming. Now, when I asked him what that was, he said he had just parallel parked successfully. That's awesome. Now, I had never heard of that, but at least he's going to pass his driving test. Me? I spent 10 minutes downtown the other day trying to parallel park, and my dad was yelling at me the whole time. It was really embarrassing. I think unless I get a smart car, I'll probably be stuck driving around in one of these for the rest of my life. Josh was complaining the other day about having to write proofs involving quadrilaterals. So maybe if I help him on his geometry, he can teach me how to parallel park. Let's start with Josh's favorite quadrilateral, the parallelogram. Now, the definition of a parallelogram is that both pairs of opposite sides are parallel. What else do we know? Well, the opposite angles look congruent, the opposite sides look congruent, but we can't assume these facts just because they look that way. We can take a bunch of parallelograms, measure the sides and angles to see that this is always true, but that can get really old really fast. But if we can prove it deductively, then we know that it is always true. You see, that's the difference between deductive and inductive reasoning. Inductive reasoning is done from observation. You take a bunch of parallelograms, measure all their angles, and you see that opposite angles have the same measure, and so they are congruent. In deductive reasoning, you take a set of premises and make a logical argument to prove something is true. We use inductive reasoning far more often in life than deductive reasoning. Wait, that could be why Josh hates writing proofs in geometry. Suppose your toilet was clogged at home. Dude, that's gross. Here are the tools that you would need to unclog the toilet. Yuck! I'd rather call a plumber. Premises are the tools in geometry to write proofs. They can be definitions, postulates, or theorems that you've already proven. Let's make sure that you have all the right tools in your geometry toolbox. I would much rather write a proof than unclog a toilet. First, we have the definition of a parallelogram. Next, there are the triangle congruence methods like ASA, SAS, and SSS. And also you need CPCTC, which goes along with the triangle congruence methods. I bet you can't say CPCTC 3 times fast. Next, we have some other theorems that you might need. First, remember when you studied parallel lines that were cut by a transversal? You probably learned that same-side interior angles are supplementary. In the figure, you have two parallel lines that are cut by a transversal, and angles 1 and 2 are same-side interior angles. So their measures add up to 180 degrees. Finally, don't forget that in the same figure with two parallel lines, you also have alternate interior angles that are congruent. In the figure, angles 4 and 3 are alternate interior angles, so they are congruent. Here's another theorem that you probably learned and may have forgotten. In the figures, angles 3 and 4 are supplementary, and angles 5 and 6 are supplementary. If angles 3 and 5 are congruent, then angles 4 and 6 are congruent. We call that the congruent supplements theorem. You can also apply the same logic to two angles congruent to the same angle. So if angles 4 and 6 are supplementary to angle 5, then angles 4 and 6 would be congruent. Time to use all these tools to prove the different characteristics of a parallelogram. Let's start with the angles. I'm going to label the vertices of the parallelogram A, B, C, and D. We want to show two things about angles and parallelograms: that consecutive angles are supplementary and that opposite angles are congruent. The word consecutive means one after the other. So we want to prove that angles A and B are supplementary, angles B and C are supplementary, and so on. We will also want to show that opposite angles A and C are congruent and opposite angles B and D are congruent. So we are given parallelogram ABCD. We want to prove angle A is supplementary to angle B, and angle B is supplementary to angle C. If we show these things, it follows that angle C is supplementary to angle D, and angle D is supplementary to angle A. We also want to prove that angle A is congruent to angle C, and angle B is congruent to angle D. Let's go to the toolbox and see what we have. Well, it's a parallelogram, so both pairs of sides must be parallel. So segment AB is parallel to segment DC, and segment AD is parallel to segment BC because of the definition of a parallelogram. I need to show that angle A and angle B are supplementary, and they look just like that picture that showed that same-side interior angles are supplementary when two parallel lines are cut by a transversal. If segment AB is a transversal, then angle A and angle B are same-side interior angles. My theorem from the toolbox said that they must be supplementary. The same holds true for angles B and C. If segment BC is a transversal, then angles B and C are the same side interior angles and must be supplementary. Awesome! I just proved that consecutive angles are supplementary in a parallelogram. Since angle A is supplementary to angle B, and angle C is supplementary to angle B, and angle A must be congruent to angle C by the congruent supplements theorem. By the same logic, if angle B is supplementary to angle C, and angle C is supplementary to angle D, then angles B and D must be congruent for the same reason. This proves that opposite angles in a parallelogram are congruent. To prove that opposite sides in a parallelogram are congruent, we need to draw one diagonal which forms two triangles. Notice how the opposite sides of the parallelogram appear in each of the triangles. So side AB is in one triangle and side DC is in the other triangle. Likewise, side BC is on one triangle and side AD is on the other triangle. If we can prove the two triangles are congruent, then we can use CPCTC to say that these opposite sides are congruent. So if we are given parallelogram ABCD, we want to prove that segment AB is congruent to segment CD and that segment DA is congruent to segment BC. We start off just like we did in the last proof by using the definition of a parallelogram. Since there are already two triangles drawn in the figure, let's prove that they're congruent. To do that, we simply have to count to 3. That is, we need to prove that 3 different pairs of sides or angles of the triangles are congruent to use SSS, ASA, or SAS. In this case, there's already one common side of the triangle, diagonal BD, and that's congruent to itself by the reflexive property. That's one. Check this out. Diagonal BD is also transversal to both pairs of opposite sides of the parallelogram. That means that you have 2 pairs of alternate interior angles, so they must be congruent. In our proof, we would write angle ABD is congruent to angle CDB, and angle ADB is congruent to angle CBD because of alternate interior angles. That's 2 and 3. Now we can say that the two triangles are congruent by ASA, and that the opposite sides AB and CD are congruent, as well as the fact that the opposite sides BC and DA are congruent by CPCTC. Now that we have all the right tools in our geometry toolbox, it shouldn't be too hard for Josh to complete his assignment on proofs with parallelograms. And hopefully he can teach me how to parallel park so I can pass my driver's license test.